Let's just. Okay. Anyways, I think that I'm recording. I hope Alam is doing it as well. If not, well, there's a even bigger reason to pay more attention to your talk. So whoever was not here will miss it. Like like in these TV shows that say we are not going to be able to broadcast this in a million years. So there you go. You can start Jinbao, and thank you.
Okay, so let me know if there's anything wrong with with the PowerPoint or something. Is it going on well?
Actually, I stopped seeing your screen.
Yeah, we cannot see your screen anymore.
Oh, wait a second. Yeah. Okay.
Hey, by any chance, do you know Gong Ha?
Huh?
Ha, yes, he was in Paris.
Ha.
I think that he was Vietnamese.
No, I have no idea.
It's just like he sent me a message and he's saying, "Dang, bro, it's now at LMU." So probably somebody knows you. I put a join us. We are there now. We'll see.
You're
And
famous.
Oh, I'm famous.
anyways, if he joins, he will let us know. You can start.
Okay, is it working now? This is
Yeah,
screen
we can
share.
see your
Yeah,
screen.
we can see it.
Okay, let's start. Oh, I still don't know what to start. I always say good morning or good evening, but like, what should I say? Good afternoon. Yeah, whatever. Good day, everybody. So, welcome to the talk. The topic of this talk is called experimental implementation and characterization of an aerosol transport system for fission products. So the title is a bit long, but I think it's very straightforward. So you can, based on this title, you can have an expectation on what you will see in the next following slides. So let's get into it. Okay. Wait a second. Why is it not working? Oh yeah, okay. So the outline of my presentation consists of four parts. The first part is motivation and research approach. So this part will present you like why we are doing this research and how we are going to do it. And then the experimental setup part. So like based on the motivation and approach. So this part will tell you some technical details like how exactly technically we are going to put this into practice, and then the results of this research, and finally the conclusion and outlook. So the first part, motivation and research approach. So, so the ultimate goal of our research group is to study the origin of heavy elements in the universe. So this figure shows different pathways of element synthesis in the universe. So light elements are mainly synthesized through successive nuclear fusion in stars, up to the iron peak. Heavier elements than iron are mainly generated by neutron capture process. The key difference is how fast the neutron capture is compared to beta-minus decay. So when neutron capture is slower or close to beta-minus decay, the pathway follows the value of stability, and we have the so-called slow neutron capture process, or simply S process. And when neutron capture is much faster than beta-minus decay, the path goes to extremely neutron-rich region. And then through beta decay, new elements are produced, and this process is called rapid neutron capture process, or R process. So for R process to happen, it requires the extremely high neutron density, much higher than conventional accelerators could provide. Therefore, R process only happens in some astrophysical phenomena like neutron merger stars. And along the R process here, you can see the red pathways. at magic neutron number around, like, for example, 126, the neutron capture cross-section drops significantly, leading to the so-called waiting point phenomenon. And nuclei around 120, 126 neutron number are extremely neutron rich and therefore extremely hard to generate under laboratory conditions. As a result, experimental data in this region are really rare and scarce, despite the crucial role they play in understanding the origin of these heavy elements. So how are we going to study this? So we want to use laser-driven ion acceleration to generate extremely neutron-rich isotopes. To be specific, the so-called fission-fusion reaction scheme. So here you can see the laser beam is focused on the production target, consists of deuterated polyethylene and thorium, and oh my god, I always have problem with this. Like, deuterium ions and thorium ions will be accelerated, and then the accelerated deuterium ions will induce nuclear fission in the oh my god, in the thorium layer of the reaction target, and then the accelerated thorium ions will undergo fission in the polyethylene target, and then both fission fragments are neutron rich, and then they can fuse together in this thorium layer, and it leading to a formation of extremely neutron rich nuclei. So this is a big picture of fission fusion reaction. So now you may want to ask, what is laser-driven ion acceleration? So this figure provides an overview of laser-driven ion acceleration. So the laser is focused on the target and ionized atoms of the target material. Based on the laser intensity, two acceleration mechanisms are proposed. So for laser with intensity in the region from 10 to 18 to 10 to 23 watts per square centimeter, target normal sheath acceleration, or simply TNSA, is dominant. The freed electrons propagate through the target, forming the biasheaths on both sides of the target, and this leads to a very strong charge separation electric field, and this field will then accelerate ions, mainly protons. And then when the laser intensity is high enough, like reaching more than 10 to 23 watts per square centimeter, radiation pressure acceleration becomes dominant. The radiation pressure of the laser pulse pushes will push a layer of electrons from the front end toward the right side of the target, and along the propagation of this layer, the resulting charge separation field will accelerate ions in the forward direction. And however, the laser intensity required by RPA is still like out of reach with existing laser systems, so it's not like so relevant to the experiments operated in our institute, but like it's a very promising way to realize fission fusion reaction scheme. So what properties of laser accelerated particle beams have? So we want to use them to generate extremely neutron-rich isotopes. One of the most important properties is their ultra-high particle density. If we can reach radiation pressure acceleration regime, we can even have solid-state like particle beam density. This density is 10 to 14 times higher than in the conventional accelerators. However, with this advantage, there are also some significant drawbacks. So among these, the strong electromagnetic pulse poses a very significant challenge for the detection of subsequent fission fragments with sensitive and highly resolving detectors like high purity germanium detectors. And also we need to meet some like stringent vacuum conditions for the laser to propagate because the laser intensity is so strong. Hey, why is it not working? Okay. So the challenge we have now, first one, we have very limited power of existing laser systems, so we can only reach the target normal sheath acceleration dominated regime. And then actually we have a lot of nuclear reactors, so we are kind of familiar with nuclear fission reactions. However, we have very limited knowledge of nuclear reactions induced by laser accelerated particles. And also we have difficulties in target fabrication. So if you still remember the figure shown in the part of fission-fusion reaction scheme, we have for this like protection target, we have this double layered target of hundreds of nanometers, which can be a very big challenge for fabrication and also radiation safety. So because we have this thorium and two layers of thoriums, and then during laser plasma interactions, this laser pulse will like destroy this target, and then the target material will be dispersed into the whole vacuum chamber, and then this can cause very like significant radiation safety concerns.
Excuse me, Jinbao.
Yeah.
May I ask you
Yeah.
something real quick?
Yeah.
You said that I'm not aware of what is the power of existing laser systems. I read in your thesis, I may have misunderstood something, but I saw that you were expecting or you obtained already. I don't think you obtained it, but it was expected or theoretically expected to get an intensity of 10 to the 20 something watts per cube centimeter for the laser, or I don't know if that was for the laser, but my question remains, what is the power of existing laser systems, the maximum that you have seen or know about?
Yes. So like actually for the mechanism of acceleration, it depends more on the laser intensity, but like also, so there will also be a problem of how well you can focus this laser beam. But for power of existing laser systems, for example, the one we have in our institute is around 3 petawatts. And
how much is that in scientific notation?
3 petawatt is 10 to 16 watts, right?
Okay.
10 to 15 or 16.
So you're still below the 10 to the 23, right?
Yeah, 10 to 23 is the intensity. So we can we can like focus it to square of micrometers.
Yes, that's what I was thinking.
So it's still around there, but still not enough.
Yeah,
So
especially
actually, this scheme was not proposed to be operated in our institute. It was proposed for the ELI, Extreme Light Infrastructure. It's a bigger light source in Europe. Like they have this 10 petawatts laser system. And if you're interested, actually China is building the strongest one. It was proposed to be 100 petawatts, so 2 orders of magnitude higher.
getting closer.
Because we are filthy rich.
Yeah.
Money bad spent, like wasted money. Everyone knows laser physics is not going anywhere. It's a joke, bro. It's a joke. It's a joke.
Yeah.
Okay,
No,
continue.
but
Yeah.
just like a last comment, you said 10 to the 18 watts per square centimeter, right? Or 16?
No, higher, around 10 to 20, 21, based on our focus.
Oh no, but the one that you used, the one that you're
Yeah,
talking about.
yeah.
Okay.
That's the intensity.
And based on your thesis, that is closer to like astrophysical processes, right?
No, that's more
Or
like, I don't know, by astrophysical process you mean.
like yeah, no, I don't. I was looking when I read your thesis. I was looking at what was the basis for which I could say, oh yeah, 10 to the 23 watts per square centimeter are a lot. So I looked and saw many like examples that industrial laser cutting is 10 to 8 something watts per cubic centimeter per square centimeter. And I think 10 to the 16, 10 to the or above were very special astrophysical processes. I don't remember which ones. It was telling like the surface of it was not magnetars, it was neutron stars. Carlos was looking at that with me. I don't remember if he knows the figure more precisely.
Yeah, no, sorry, I cannot tell, but the, the the thing is that, and it is still not clear to me because you're putting it in here as challenges. So, uh, in terms
No,
of
yeah,
intensity,
no.
I mean, could you say that you are in the regime where these techniques could be applicable or not? Probably that's the thing that we can summarize it at the moment.
Yeah, okay. So in this way, like the very good one, fission-fusion reaction scheme is still not like beyond reach now.
Okay.
Yeah, because we need to reach RPA, so radiation pressure acceleration. With
Yes,
that,
because
we can have this solid state like particle beam bunches.
yeah, because it's more efficient, right? The conversion between the energy that you're supplying and the intensity that you're getting.
Yes.
Okay.
And also with because with TNSA you can understand it this way, like the energy of particle bunches scales with the square root of the laser intensity, but if you can reach RPA, it will square with the intensity itself.
Yeah.
So like we have better conversion of laser energy into particle energy bunches, and this will be related to the cross section of nuclear reactions, for example.
Yeah.
So we have higher particle density and we have higher energy. So with higher energy, we have larger cross section, and then we have higher probability for nuclear reactions to happen, and also we have higher particle density, so we have more yields and better signal to noise ratio.
Mm-hmm.
Okay.
Sure.
Okay, if there's no more questions, then Jinbao, sorry for the interruption. You can continue.
Yeah, sure. So one last question, as I said, for such intense laser pulse to propagate, we need to put a whole system in the vacuum chamber instead of let them in the air, because it will ionize the air and we lose energy. So it will, and with like very strong electric EMP, so it's very hard to detect those fission products, especially with those short-lived. Like for long-lived, like several hours or days, we can put a film to collect those fission products and then put them in front of the detector. But for those of tens of seconds, and usually they are more interesting and also very important. So this will also be a challenge in product detection. So how are we going to solve these problems? So just step by step. So we have a combination of compromises and solutions. So for compromises, like with the laser intensities and with and other like target fabrications, which is still a technical challenge now we cannot overcome. So we can begin with proton induced fission, and these protons can be accelerated by our existing laser systems. So we just irradiate the like aluminum or plastic foil. So and then the protons will be mainly accelerated by this TNSA mechanism. And then for the detection of products, which is also the key point of this thesis project, we draw on the well-established method in radiochemistry. So because in radiochemistry, they also want to detect the nuclear reaction products in the core area of the nuclear reactors, which is also inaccessible for detectors or for scientists. So they build on this gas jet system. So they put in gas into the source area and then transport those fission products out of that area, and then these fission products are trapped by a filter, and then they decay, and this filter is usually in front of the detector, so we can detect these transported fission products. So usually they only have gases or gas mixtures, like for example argon and helium mixture, but this gas mixture usually can only transport volatile nuclei, for example xenon and iodine, but like some metal species, of course, they are non-volatile, and also they are very important. So how are we going to do this? We just add aerosol particles into this gas flow. So these aerosol particles will capture these non-volatile species and then transport them out and then get trapped by the filter. So building up this aerosol system is the main job of this thesis project. Are we okay with the first part?
Sure thing. Yeah.
Yes.
Okay. So let's have a look at experimental setup. So this figure shows you the aerosol system. First, the aerosol system overview of the aerosol system. So the aerosol is generated by this aerosol generator here. So here is a nozzle, and we put on this pressurized air here, and then this pressurized air will draw these solutions in the reservoir below, and then tear them into small droplets, and these droplets will then be pushed by the gas flow into this aerosol dryer, where those solvents will evaporate and the salts will recrystallize and then disperse into this gas flow. And then after this dryer, they go into this electrostatic classifier. So this one is used to classify the aerosol particles based on their electromobility. So and also related to their particle sizes. So they at one time only particles with a certain size can pass this classifier, and then they go into this particle counter. So this particle counter is equipped with a laser counting system, so that it will count the particles contained in this gas flow. So by selecting different particle size of classifications and then count them, and the whole aerosol size distribution of this aerosol flow can be obtained. And this system was first built up in the preparatory laboratory and then moved into our real experimental cave for experiments under real conditions. So the main difference between the preparatory laboratory and the experimental cave is actually the transport tubing between the aerosol dryer and the classifier. So in the experimental cave, this part will be more complicated, which will be introduced in the following slides. And now this, as we said, this part shows an overview of the whole transport system in the experimental cave, and this system can be operated in two modes, namely linear mode and loop mode, and can be switched between these two modes by adjusting bypass valves showing at the connections here. So, and both modes will be introduced in detail in the following slides. So firstly, the loop mode. The loop mode is mainly used for transport of volatile isotopes with using only gases, so without aerosols. So after this gas feeding, and by adjusting bypass valves, the whole setup will be sealed, forming a closed loop, and then the transport gas will circulate inside this whole loop, driven by a membrane pump here. And when the gas passes through this target container, and then those volatile fission products will be transported and then captured here by this charcoal filter, and then detected by the high purity germanium detector. So the advantages of the loop mode is you can see it's sealed, so we don't need to worry about about the capture efficiency of this filter, because even if there are some radioactive species left, they are still sealed inside this whole loop. However, the main disadvantage is the requirement of excellent gas tightness, because when they circulate, you don't want to lose those gases and also pressures. And also you can see here so many connections, and during the real process building up this system, it was really a catastrophe. Yeah. And then the linear mode. The linear mode is mainly used for aerosol transport. So here, this part is where the aerosol generator and dryer. So the gas, the pressure, mainly the pressurized air will be applied to the generator, and then aerosols will be generated and then passing through the whole setup, and then the aerosols pass through here and then transport those non-volatile species. And also the aerosol counting part is also integrated into this system, and they were located right next to this filter in the real case. So like this allows us to do the aerosol size distribution scan prior to the real transportation, so we have a better understanding of like what the properties of aerosols arriving at this filter. So some parameters of the transport system will be interesting, so we can understand better of this transport system, and also know better how well it can help us detecting these fission products. So the transport tubes, we use stainless steel because we want to get rid of those static charge accumulation along the tubing walls, leading to the particle losses. So the whole length in the experimental cave is around 16 meters, and the inner diameter is 4 millimeters, which we can by calculating this, we have the volume of 0.14 liters. Here we used two-third effective area. This is based on the consideration of the velocity profile of this this gas flow inside this cylinder-shaped tubings. If you know something about like fluid mechanics, I think you will understand this. And then with target container, because with this in this experimental cave, we also need to fill in this extra volume introduced by this container. So its parameters is also here, and its volume can be calculated at 0.09 liters. So the aerosol flow, the volumetric flow rate based on measurement is 2.1 liters per minute. So the whole transport system is around 6 seconds. So this really allows us to detect those short-lived isotopes. So next, this one shows us the setup inside our vacuum chamber, where the laser-driven ion acceleration takes place. So the laser is first focused by an off-axis parabola here. So it's made of copper, and then here they are focused on this on the target mounted on the target wheel, and here is a 6-axis hexapod allowing us to do fine adjustment of laser focus to put the target into the focus. And then accelerated particles either travel a short distance to this fission container, so they can induce fission of uranium there, or they can go first to this ion diagnostics. So in the real experiment, we will first have a shot to this ion diagnostics to have a check of ion properties, and then if we know, okay, everything is fine with ion beams, and then we drive in this target container and then let the nuclear fission happen. So here's a more detailed schematic of the target container. The uranium targets in two groups of three are housed inside it, and the gas flow, either with or without aerosol particles, will pass through continuously during the experiment to transport fission products. The two thin titanium windows here are used to separate the inner volume from the vacuum environment outside, and this 25 micrometers thickness can also minimize the proton energy loss. It's around like it's just negligible. And then in the offline benchmark, so without like laser-driven acceleration experiments, we use a spontaneous Californium 252 source for the offline benchmark, so we can also transport some fission products. So the results of this thesis. So firstly, I did some aerosol characterizations in the preparatory laboratory after building up these aerosol systems. So what you see here is the size distribution of potassium chloride aerosols measured in the preparatory laboratory, and the transport length was about 2 meters and generated and an operating pressure of 2.4 bar, and for different potassium chloride solution concentrations. So firstly, overall, you can see all size distribution exhibit a peak in particle diameter in range of 30 to 50 nanometers, although for some solution concentrations, the distributions show a shoulder or double peak structure. In addition, with increasing potassium chloride solution concentrations, the particle number concentration, see here on this y-axis, increases across almost the entire particle size range. At the same time, the size distribution become broader and shift toward the larger end. At low solution concentrations, the size distribution exhibit an relatively ideal log normal distribution shape. However, the solution concentration goes higher. The shape of distribution get distorted and developing some like shoulder or double peak structure. And sufficiently high solution concentrations further, like for example, this area here, further increasing the solution concentration has a less significant impact on the overall size distribution shape. Sorry, I forgot those bullet points.
May I ask you something real quick, just to make sure that I'm following you? There is this thing where like you have your laser and you're trying to excite particles in order to have fission and fusion one after the other, right? That's what you said in your first. That's what I understood.
No, in this thesis we don't have fusion. We only have nuclear fission of uranium.
In the case of like higher energies, you would expect having fusion as well, but in this case, you don't.
No. The nuclear fusion will be expected with like fission-fusion reaction scheme with higher laser intensities, because we need those double layered targets.
Okay.
And here, let me go back a little bit. And here you can see laser is focused on this target, and then protons are accelerated, and then they just go into this target container, and here only uranium is here. And then these accelerated protons will induce nuclear fission of this uranium. And if we want fusion, that's actually earlier.
Here. No, Yeah,
Yeah,
I
you can see
understand
here.
that you need like a stronger, like more potent lasers in order to obtain fusion. I'm just trying to wrap my head around the whole process. So in this case,
Yeah, okay.
you only get fission, and you use
Yeah,
the aerosol to transport the results of that fission into a container when you can further analyze later, right?
yeah.
Okay, so why it is important to see the distributions that you were seeing in the last slide that you were looking at? Why it is important to know these distributions and concentrations? I mean, of course, you have to do a characterization, because you cannot just like put on an aerosol and say like, oh no, yes, an aerosol is just any aerosol. But why it is important to know the distribution with size? If it's too big, something happens. If it's too small, something else happens.
Yes, because this the capture efficiency of fission
Oh, by the way,
products. Yeah.
sorry. Um, we don't have premium for Google Meets, so it's possible that at any moment the the call is gonna end abruptly, but we're gonna go back to it again. Okay?
So we need to restart this meeting.
Yes, yes.
Yeah, that's actually my fault because I have premium on my account, but not on the one that we're using to present this. So it's a nightmare.
Yes, it will end in 9 minutes.
Yeah,
Okay.
but take your time. We will just restart where we left, okay?
Yeah, yeah.
Yeah.
Okay. Well, yeah. If you can answer that question in the time that you have. It's good.
Okay. So what do we do now?
You can answer my question if you want.
Yeah. The importance of this, because the capture efficiency of fission products mainly depend on the total particle number and size of these aerosol particles. And during the generation of aerosols, we have two parameters to play with: the operating pressure and solution concentration. So of course we want to see how these two parameters will affect the aerosol properties, the generated aerosol properties. So we can have like better control of in the future of transport of fission products. So you know how these parameters will affect the properties of aerosols, and then you can then relate these properties of these parameters to the results of your fission products. So you can see, okay, based on this, like maybe, yeah, for the following results, we know that the operating pressure is not very important, and so the main factor is the solution concentration. So we can try to find, okay, with this solution concentration, we have the best transport performance with aerosols.
Does
And then yeah,
huh? Continue? You know, you continue.
and then we can know, okay, based on this solution concentration and this size distribution, we know, okay, with this operating pressure and solution concentration, how this aerosol look like what which size has the highest solution, highest particle density for like this.
Mhm. Mm, okay, I still have some doubts, but I'll let you finish because I feel that I stopped you before you could continue. Uh, so I'll rather let you finish, and if you know, like, just keep presenting, and if the meeting stops, like, we'll just go back again. Okay?
Okay. Okay, this, let me see, this in addition to size distributions of, as I have just said, the total particle number is also very important to the transport performance. So this figure presents the variation of total particle number as a function of solution concentration and at different operating pressures. So it can be seen that with increasing solution concentrations, the total particle number in the low solution concentration regime increases significantly. However, like the size distributions in the high concentration regime, this trend becomes rather weak. You can see mainly this area here, and also on top of that, at focused no at a fixed solution concentration, the effect of operating pressure is more complex, so no clear dependence was observed, and the difference remain negligible if you consider the experimental errors. So this figure is about median diameter of the aerosol particles. So the overall trend is similar to that of the total particle number. So when the solution concentration has major impact on the median particle size, while the effect of the operating pressure remains negligible. So a small conclusion here. So for solution concentration, is the major impact on the final results. So with higher, we have broader size distribution and more larger particles, and also more particles. With operating pressure, its effects are negligible and no clear dependence observed. So, and those are the results in the preparatory laboratory. So based on this, we can know that if we move this system to the experimental cave, we just need to recharacterization at different solution concentrations with a fixed operating pressure. So here this one shows the results at the experimental cave. So we can see here the overall trend is similar. So with higher solution concentration, the distribution becomes broader and shifts toward the larger end. But in the meantime, we see that the distortion in size distributions was somehow suppressed. Only slight shoulder structures are visible here.
And
sorry
for interrupting again. This is a similar plot to the one that you had at the beginning of your results, right?
Yeah, but this one is the result in the experimental cave, so with a totally different transport path.
Oh, okay. Yeah, because I was gonna ask, probably like because of the it is a little different. What do you think you didn't found? Probably you were gonna say it, but asking anyway. Double peaks here. In your first one, you had double peaks. Why is that in your experimental cave you didn't found double peaks in your distributions?
Yeah, actually, this question was discussed in the thesis, but it was not shown here because it will be too detailed. Like, I found that in the experimental cave, it's very easier for those smaller particles to get lost, maybe due to diffusion or some stochastic processes. And if we go back to this result, we can see this. For the double peak structure, the first peak is mainly located in this like relatively small area. Maybe yeah, it was only my guess, but due to this loss of smaller particles, so this the first small peak, it should be in this area, get somehow suppressed.
Okay, but is it that it was discussed? Is there any? Okay, the call is gonna end soon. Is there any? It was thoroughly studied about why do you think, or what did the people you work with thought that this was caused to diffusion, or it was just like a out of my head explanation? Because that's what researchers do sometimes. Like,
yeah. You mean how those smaller particles get lost?
no, what? How do they came to that conclusion that it was probably diffusion or stochastic processes?
Yeah, because they are smaller, so those like diffusion or those like I can't think of that term. Term. Yeah, they have.